So good afternoon, everyone. My name is Mar, and the title of this presentation is Black Lion, a software simulator for heterogeneous spaceflight and mission components. Before anything else, I would like to acknowledge the co-authors who are not here today, Patrick Keneally and Dr. Hans-Peter Schaub from the University of Colorado Boulder, and Scott Pigot from LASP. So before anything else, let me explain this long title. In plain words, Black Lion is the communication architecture for what is known as a soft SIM. And this soft SIM is being built in order to support flat-sat testing of an interplanetary spacecraft mission in which LASP is participating. So in the context of flat-sat, we have multiple mission components interacting with each other, like we would have the ground system, the single board computer, the flight software running on an RTOS on that SVC, and we would also have simulation model for the dynamic kinematics and environment in order to test your flight algorithms in closed-loop simulation. So similarly, in the context of a soft SIM, we want to have exactly the same components, but all of them virtualized. So we would have a ground system emulator and a single board computer emulator. And in today's presentation, I'll be talking about the communication architecture we are building in order to have all these software components to actually talk to each other. And it is important to understand that all these software models are essentially standalone applications that they don't know about each other because they were never meant to be part of a soft SIM, and that are completely heterogeneous. They are written in different programming languages, they run at different speeds, and some of them are just commercial off-the-shelf products that are available to us and that we want to take advantage of. So the whole point of Black Lion is to actually connect and synchronize all these components while being completely transparent and abstracted from the internals of each component or each node, such that you can essentially plug and play with your models of choice. So throughout today's presentation, I'll be talking about the strategy we're pursuing on this communication layer in order to achieve the desired transparency and abstraction. And let's take a look at the outline. So we'll first review the concept and motivation for a soft SIM. I'll then describe the specific mission components that we want to include into the Black Lion soft SIM. Then we'll take a look at how heterogeneous these components actually are, but how we can still achieve communication while being not intrusive at all to the internals of each component. Then I would like to highlight the modern flavor that we are giving to this communication architecture through the adoption of what is considered modern software technology and techniques. And then we'll get down into the actual workings of the communication hub. And of course, we'll end up with some conclusions and future work. So let's start by the beginning, soft SIM concept and motivation. So the whole purpose of a soft SIM is to test the onboard flight software, which is also one of the purposes of flat-sat testing. When I say onboard flight software, I essentially refer to the binary image that is loaded to the spacecraft. And the scope of the flight software testing, either in flat-sat or in soft SIM, is to essentially analyze the flight software response to, in answer to dynamic stimuli and conditions in a spacecraft operational environment. So where soft SIM does not replace flat-sat, it can leverage some of the work and avoid bottleneck in the sense of limited hardware components, like hardware that is needed by different mission groups simultaneously to perform different kinds of testing, and also bottleneck in the sense of timing, because if the flat-sat structure is not put together on the time that was scheduled, well, all the testing also starts falling behind. So in this sense, the soft SIM provides a cost-effective, flexible means of performing early-on testing. So providing some sort of literature review, there are currently several missions that are using soft SIM to perform testing, and there are different flavors of architectures. Some are in-house solutions like ours. Others make use of Lockheed soft SIM, which I believe they are the ones who gave the name to this concept. But all of them have a common functionality, which is to test the modified flight software executable in a software-only environment. So now that we have reviewed the general concept of a soft SIM, let's talk about the particular one that we're trying to develop. So in last year's workshop, my colleague from LASP, Scott Pigot, talk about the ADCS development we are doing for this very same spacecraft interplanetary mission that I've already mentioned. And as a quick recap, Scott introduced Basilisk, which is an open source software platform for prototyping and testing flight software in realistic closed-loop dynamics. And Basilisk is exposed to the user as a Python application, but the source code is all in C and C++. And another relevant feature of Basilisk is that it uses a message passing interface between the different tasks and processes of flight software and simulation. And this message passing interface makes it very easy to essentially take the flight application once fully developed and migrate it out of the Basilisk development environment. And in particular, last year, Scott discussed the transition of the flight application from the Basilisk environment to a CFS application that is ready to be embedded into a flight target running the standard RTOS. So once more, last year, we only focused on the ADCS development, which included the CFS and ADCS application, and also the Basilisk spacecraft models that we're using in order to test these algorithms in closed-loop dynamics. So now we have decided to move one step forward and essentially expand the simulation coverage into multiple nodes or multiple mission components in order to allow simultaneous fast testing from multiple engineering groups. Not only the ADCS folks, but also the ground system group who want to test their ground scripts, or the fault management team who like to throw some corruption to the sensors and actuators models and also to corrupt the flight software packet. So with this purpose of simulating multiple mission components is where the idea of a soft sim begins. And now I would like to provide slightly more insight on the specific components that we are particularly interested in integrating in our soft sim. So the first one is the ground system emulator. An example of this kind of virtual model would be Cosmos, which is open source, although it's not the one that we're actually using. In any case, the ground system emulator is supposed to use the same ground scripts as the physical one. It sends commands out, it expects telemetry in, all in the form of CCSD packets that are mission specific. The second component is the virtualized model of the single board computer. For instance, QEMU, which I believe is also open source. And inside the processor board emulator, we essentially find the modified flight software executable and also FPGA-like registers, because we are all interested in simulating these registers and providing the functionality. What we currently have is just a memory map for the input and output of raw binary data. The third node that we want to integrate is the spacecraft models, which, as I've already mentioned, we are using Basilisk. And Basilisk is providing us with hardware models for sensors, actuators, and power computer unit, and also provide us with high-fidelity dynamic, kinematic, and environment models. And the last component that we want to integrate here is visualization, which in our case is just an in-house graphical user interface, or GUI, that we're developing using the Unity game engine. And essentially, the visualization is just supposed to reproduce the spacecraft physical behaviors as determined by your simulation software, which in our case is Basilisk. All right, so now that we have overviewed the different components, it starts becoming more clear how heterogeneous these components are. And this is, of course, a challenge in terms of communication. So as a quick recap, all the nodes are essentially standalone programs. And indeed, the particular nodes we're trying to integrate are written in different programming languages. So our ground system emulator is an in-house inherited solution that is written in C++. The single board computer emulator is a slightly modified version of QEMU, which ends up being a combination of C and C++. The Basilisk spacecraft models, although they have the source code in C++, they are exposed to the rest of the world as a Python application, so we have to deal with Python. And the visualization is in C# because of using Unity. And not only the applications use different programming languages, but internally, each application wraps the data in different structures or packets. For instance, the ground system emulator uses CCSDS packets with a very specific format. Basilisk has defined its own message structures or packets as well. And if we take a look at flight software, what is writing inside the FPGA-like registers is just raw binary data. So all these differences between the nodes are essentially facts that we need to deal with if we want to establish the desired communication. And when I say desired communication, I mean different things. First, transport of binary data. We want to share bytes between the nodes. Second, serialization. Each node needs to know how to translate the received bytes into structures that can then manage internally. Three, we need synchronization. We need all the nodes to step forward simultaneously, so in lockstep. And four, we want this communication to happen through a dynamics connection map. Essentially, this means that we don't want each of the nodes to have a static IP address. So the less static parts we have, the better. So in order to achieve transport, translation, synchronization, and dynamicity of the connections, the strategy that we have chosen is the following. So Black Lion is composed by a central controller and two APIs that are attached to each of the nodes. So the central controller is the one and only static point in the network. It acts as a synchronization master and as a transaction broker between the nodes, and it's written in Python. The first API we find is the delegate, and essentially it manages sockets and connections with Black Lion. It's the same script in all nodes, and we have developed and integrated Python and C++ versions as required by the internal scripting language of each node. And the second API we found is the router, which essentially has not a specific callbacks in order to route data in and out of the node internals. So essentially what it would do is to gather node internal data, translate it into a common format that would be understood by the rest of the communication system, and make it available to the delegate who is ready to ship it off through the sockets. So in order to explain this idea better, I would like to use a human language analogy. So essentially, each node is an individual who has a different mother tongue language, and the router acts as a translates from the individual's language into a common one, which would be English, but is the delegate through the sockets who actually speaks out loud and communicates in order to yield a proper English conversation. All right, so before getting into technical details of the communication hub, I would like to highlight the adoption of modern software technology and techniques that is being a critical part of our effort. So in terms of technology, we're using several open source cross-platform cutting-edge products like ZeroMQ message library to transport data in a way that is fast, reliable, and protocol independent. We are going to use Google protobuffers for efficient marshalling and marshalling of data. We are using the spacecraft simulation framework for high-fidelity dynamic models, and we are using the Unity game engine for our graphical user interface. In terms of techniques, we have adopted a component-based development, so we integrate node by node, and it's very easy to just swap nodes or add new ones or remove existing ones, thanks to this idea of a dynamic architecture in which the central controller is the one and only static piece, and the nodes or the components essentially become dynamic clients that can just come and go on the fly. Furthermore, we're also embracing agile programming through continuous delivery to mission users from each engineering group, immediate feedback integration from these users, and all of these essentially yields to very fast building, testing, and deployment cycles. All right, so let's now get into the actual workings of the communication hub. So a critical part of this communication are sockets and connections. And first, we're going to take a look at sockets. Essentially, we're using three types of ZeroMQ sockets to move data around. The first type of ZeroMQ relation is request-reply. So the controller has a rec socket for each of the nodes that is instantiated in the soft SIM. and it uses the rec socket to make requests, right? And each of the nodes has a rep socket that receive and parse the request, do something about it, and then reply back saying, hey, controller, I'm done with your request. So then we use twice the publish-subscribe socket relation. So each of the nodes has a pub socket to publish nodes' internal data, and the controller has a front end with a sub socket that subscribes to the messages from all the nodes. These received publications are then routed to the backend, which is also inside the controller, and the backend republishes this message. Back into the nodes, each node has a sub-socket that subscribes only to the message the node cares about, and of course it receives those messages from the backend republishing. So we have seen the socket types, and now let's talk about the connections between these sockets. So essentially, having a front end and a back end in the controller is what is allowing us to have only one static piece, which is the central controller. So in this sense, the central controller acts as a static server. It binds to a static IP address, and within this address, it uses 2+N ports, so a front-end port, a back-end port, and a command port for each of the nodes that is instantiated in the SoftSim. Thanks to the fact of using 0MQ, all these connections are protocol independent. In regard to the nodes, through the delegate API that is attached to them, each of the nodes essentially becomes a dynamic client. And we see this dynamicity in the fact that the nodes connect to a certain address and port instead of binding, which is what the controller does. So with this strategy, the server is always required, but the clients are just independent entities that they don't rely on each other for any kind of transaction. So I've introduced the request-reply relation between the controller and the delegate. And the requests that the controller makes are nothing like spacecraft commands. They are only commands related to communication and synchronization, so they only make sense in the context of a SoftSim. And now, let's now take a look at the specific commands that we're actually making. And it's important to say that some of these commands come in the form of multi-part messages containing more data with them. So the first request is a start message, which is multi-part, and it also contains the address of the controller's front end and the address of the controller's back end. So when the node receives the start request, essentially it self-inits itself. It connects the PAP socket to the given front-end address and the sub socket to the given back-end address. The second request is a known message, which essentially means, hey node, which message names do you want to subscribe to? And when the node receives this request, essentially it looks to itself, and it replies with a list of the message names that it's interested in subscribing if there is actually some other node that can publish that data. The third request is match messages, which is also multi-part, containing a list of the message names that the other nodes want. So essentially, the controller is asking this particular node if it can publish any of these message names that the other nodes have asked for. So the node, once more, looks internally and looks for a match, and it replies with a list of the message names for which it has actually found a match. So the next request, it deals with synchronization, and it's a tick signal that also comes with a delta time, and this delta time essentially is the length of the next time step. So when the node receives the tick signal, essentially is when the exchange of data happens. So there is a publish and subscribe in all the nodes, and then each of them steps its internal simulation forward for this certain delta time. The last request is finish, and essentially is used in order to close connection, close sockets, clean up everything, and leave the application clearly. So let's now take a look at everything that is actually happening between the tick and the talk reply. So when the node receives the tick, it publishes its internal data. So this means that the router collects the node internal data, and the delegate sends it out to the controller's front end. The front end routes it to the controller's backend, and in the meanwhile, the subscribed sockets in the nodes opens and starts listening, such that the delegate can receive this external data, and the router can write it back into the internals of the application. When the nodes are done publishing and subscribing, then they step simulation further, which just means execute your internal process during delta time. And in this execution is when they essentially generate new data that they may publish at the next TikTok signal. So because all the nodes are standalone applications, so are different processes, and they run at different speeds, the TikTok strategy is what will allow us to essentially become in lockstep. And let's now take a look at once more at the specific 4 nodes that we want to integrate in our SoftSim. So both the flight software and the spacecraft dynamics have a synchronous nature in the sense that they run in cycles or rates, but the flight software is running in real time because of the fact that it's being executed inside the single board computer emulator. And the spacecraft dynamic models are running faster than real time. In contrast, the ground system is asynchronous in the sense that it operates on discrete time events, and the visualization is just not a critical component to maintain in lockstep because it's essentially just a listener. And depending on the asynchronous or synchronous nature of these nodes, the step sim call that happens between the TikTok has a different meaning. So for flight software and dynamics simulation, who are synchronous nodes, step sim means to run as many cycles as there are within that delta time. For the ground system, what we are doing is just checking if there is any command scheduled between the previous time and the current time. And of course, it's up to the user to make sure that the delta time set is small enough, or that commands that conflict between each other are not requested within the same time step. So the key point here is that although the nodes run at different speeds, the virtual time elapsed is exactly the same. So this means that if one node finishes quicker, it sends the talk and waits for any request from the controller, because the controller won't proceed until it has collected the talks from all the nodes. The speed of the SoftSim is essentially driven by the slowest of your components, which in our case, it would be flight software QEMU, if instantiated. So I'm about to finish, and I would just like to make one last comment on the capability we have of running BlackLion in a distributed system. So we have tested multiple machines running different operation systems and all talking to each other. And what's nice here is that this is a capability that we have essentially got just for free, thanks to the fact of using the modern technology that I've introduced before. So conclusions and future work. As a conclusions, I've talked about BlackLion, a communication architecture for a SoftSim that is characterized by the abstraction from the nodes diversity. We have developed and integrated APIs that deal with multi-threaded and single-threaded nodes, Python, C, C++, and C# nodes. We have out-of-the-box multi-machine functionality, cross-platform compatibility, and what makes BlackLion interesting is the flexibility and the scalability of the architecture, which is granted by the adoption of modern software tools and techniques. As future work, we would like to add some more functionality to the central controller, which is essentially dynamic discovery of nodes, because we still have to figure out which is the IP address of the server, and then hardcode this line into the delegate of all the nodes. We also want to be able to handle node failure gracefully. We would like the central controller to deliver the initialization script such that it can say like, hey, everybody in orbit insertion mode to start the simulation. We would like to include a direct pipe for introducing injecting faults into the spacecraft models, like the sensors and actuators, and also to the flight software packets. And we would also like the central controller to be able to handle multiple simultaneous soft-sim runs. And this means tracking of each soft-sim session and of managing the logging of the exchange data. So thank you very much for your attention. And if you have any questions, I'll be very happy to take them.
Thank you. Thanks, Phil.
Yes, I saw you were using Google protobufs. Would you consider EDS? For message definitions, the EDS instead of Google protobufs? Or did I miss that?
Yes?
The EDS.
Oh, okay. Yeah, the
which is
electronic data sheets.
Exchange, yes.
I'll check them out because I mentioned that we are going to use Google protobuffers. We have not implemented that technology, so we are open to use other, yeah.
You just got a customer, Jonathan.
So with the time synchronization, do the specific applications on each node have to know how to deal with that? Like, or could you, like I'm thinking if you just plug Cosmos in as your ground station, and it's going to get time, normally from the system itself, are you altering the system? I'm still a little unsure exactly how the pieces know that they're supposed to wait.
So it's not, what waits is essentially the tick-tock. So they won't exchange data. They will wait for that, but the application in the background is still running. Does this make sense? It's not waiting, doing nothing. It's just like the sockets and the connections and the communication of the soft-sim that is sort of in standby, but the application is still running on the background.
All right. We need to do it quick because we are running out, but of time.
We had done an integration example of several large-scale simulations that were written independently, not nearly as well organized as this, but basically the same principles. And the issue was how you got any simulation that had its own idea of time advance to do it the way you wanted it to. In other words, each one has its own style because other people wrote these. We didn't write any of these.
Yeah. So we are indeed running with a few difficulties on running with time on dealing with time with QEMU because we don't have the controllability that we wanted. QEMU, for instance, we have like some timers there, and yeah, we won't have like perfect control of the timing.
So here's a challenge. They gave us the code for these things the Monday morning of a Monday afternoon demo.
Sounds challenging.
It worked. We had stubs in case we couldn't make it work, but it worked.
Autonomous vehicles. Okay.
All right.
Mar, thank you very much.
Thank you.
Yeah.